So we are now going to, boy, that was a long introduction, but we're going to go into simple linear regression. Thank goodness it's, quote, simple, which is the first and probably the most important section in the book in week 5. Week 5 is mostly about linear regression. And by simple linear regression, all we're really talking about, I want to be clear on this, is if I have, let's do the simplest case. I have a y that's a number, and I have an x that's also a number. Okay, that's the case that we're going to work in. We're not going to work in any other cases right now. Later we'll work in different types of cases, how we do regression for that. Okay, but for now we have this, and it could be I want to know how my cycle time varies. Oops. How my cycle time varies by the amount of manpower I put into, or sorry, not manpower. Sorry about that, folks. People power. People hours I put into my process. I might want to see if my cycle time decreases as I put more people into the process. Or I might want to see how if I were an environmentalist, I might want to look how the ambient temperature of a pond might vary by time of the month, or by external heating from a underwater power facility that's nearby, something like that. Okay, so we'll look at a few of these cases, and what we're really trying to do is, if I have an x and a y, and I go out and I collect a few ordered pairs, and that just means for every x I collect a y. So for example, if I was looking at heights, maybe I also collect the weights of people at the same time. So if I have the height, I'll write down mine. Maybe we'll also collect the weights on a good day. I'm 175. On a bad day, I'm quite a bit more. But anyway, and so forth. So we collect them both at once, and maybe somebody else is 6 feet tall and 202 pounds, and so forth. Those points would be put as ordered pairs, put up here, and I'm just making these up right now. There's no rhyme or reason to this. And in linear regression, what we're trying to do is we're trying to fit a line to this particular plot. Now, you probably learned this in high school, and so it may be really old history, but how do we, essentially, the theory is essentially, how do we figure out the best line, and when do we know whether a line is reasonable or not, and what can we do then with this line? That's what linear regression is all about. Okay, so that's what we're doing. To do this, I think what it makes sense to do is, let's go through a full example. There's a few things that I've learned over time. I want to go through an example. Whoops, I'll say the process. So if you're doing this for real and you're going to be a real modeler, let's learn a process for taking the baby steps of putting together a linear regression. The first thing is, we're going to plot the data. Plot. Choice is here is it turns out a scatter plot. In Excel, this is called an XY plot. In some ways, that's a nicer name. We're going to make a scatter plot, and we're going to learn how to read a scatter plot, because they can be kind of like a Rorschach test. Okay? The second thing is, then we're going to build our model, which amounts to fitting the best line that we can. Here's another line that maybe we'd have with x and y, different x, different y. Maybe that would be a line that we want to fit. Okay? But we're going to build that model. The next thing we're going to do is we're going to, being good analysts, that's not enough. We also are going to check the adequacy of the model. We'll learn how to do that. Of the model, we'll find that there's something called R squared. And finally, we will validate the model. Not the same thing as checking adequacy. Validating means, are the assumptions met? This we'll find out is checking residuals. And then finally, we will use the model for prediction. The mistake that we don't want to make is to go from here, which is, say, ground zero, to here directly, okay? Because if you go from here to here directly, you often make big, bad mistakes. Plot the data first. That's probably the most important thing. And then we'll go ahead and build the model, validate it, check it, adequacy, and do all that. You'll find that if you do this, it doesn't really take all that much more time to do this, but you'll often catch yourself on fitting some things that could be problematic. So let's take a look at this through an example. And the example that I want to do is the one that's actually on the file that's in your book, and then we'll go through step by step and actually do it in a little more detail. I'm going to close this down, and this down, and this down. Okay, but not this. And this down. Okay. And we'll do this first one in Excel Stats, but there's Minitab throughout, so you should feel free to be able to do Minitab. This is the example of can we predict can we predict gas mileage by the speed with which I'm driving a certain car? So in this case, what we did was we took a, no, not that. That's not where I want to be. There we go. Look at me. Okay, get rid of you. What we did was we took a specific car, we gave it out to different people, had them run on a test track, and we checked gas mileage as a function of the speed that they drove the car. And the question is, can we use speed, x, as a driver of gas mileage, which is our y? You'll notice that this is a num, and this is a num. Okay? So let's go through the motions, build a model, and then see if we can use it for prediction. Okay? So as I said, the first thing we ought to do is to start out with a scatter plot. So let's go ahead and do that. Luckily in Excel Stats, it's just a question of choosing the right analysis, which is 2num. Okay, and here we go. Here's our scatter plot right here. Now you may need to change the scale, which is fine. I'm going to go ahead and change the scale. All right, so the first thing that we ought to note is when we look at a scatter plot is there's no outliers, and we'll look at sort of the form of the scatter plot. In this case, it looks to me as if it's kind of a line that goes from high to low. So I'm going to just draw that in. My guess is that the rest of you see this as well. I'm just going to draw that in. That's kind of the line that I would draw if I were going to say what's the best fit to the data. That's kind of what it looks like to me. And I would also note that it looks pretty strong. The points look pretty tight around there. That's good. That makes it easy for us to predict. Okay, and I've also noticed that the direction is down, not up. It has a negative slope, not a positive slope. Those are all things that you can notice from the scatter plot. All right, that's what I notice on here. Now, because it has a pretty tight line, I can go ahead and do a linear regression. That's cool. So I'm going to go ahead and do that. I'm going to go ahead and build the model. It's pretty straightforward. Oh yeah, I want to get rid of the control spreadsheet. Oh, that's what the problem was. Okay, so I'm going to go ahead and build the model. In Excel Stats, it's just a question of clicking on the very next tab, Correlation and Linear Regression. And bam, there it is. Here's the model that I built. Pretty easy. Now, we're actually going to check something in order to build the model, and that is this right here. we're going to check two coefficients. We're going to check the p-value for the slope is equal to 0 versus it's not equal to 0. So I need to choose the right alternative. That's a very small p-value, right? Which means that the null must go, whatever that is. We'll talk about what that null is in just a second. And then over here, that's also pretty slow, or pretty low. What that amounts to is that the slope and the constant need to be in there, and that it's a significant fit of the model. Now, it's a weird hypothesis test, but the way that we interpret it is as follows. Let me get rid of that again. The way that we interpret it is as follows. The slope right here is significant, so we're going to keep the slope, and the constant is significant, so we keep the constant. So our model is we keep this term and we keep this term in our model. That's the test that we just ran. Now, that was pretty boring, but we'll find out that when we have multiple regression, we're going to add additional x's, and going through, we won't find that every slope is going to be significant. So we'll chop out some terms that don't really contribute to our model, which is good. We don't want to keep terms that are just kind of bollocksing things up. So that's it. We check the p-values on the slope. So that's good. We did that pretty quickly. Let's move on to the third piece, which is evaluating the adequacy of the model. We value the adequacy of the model by looking at a term called r squared. Now, r squared is interpreted as the percent of the variation in y explained by x. Okay? So, in other words, how much does speed account for the differences in gas mileage that we see? And this high r squared, it turns out that this can be between 0 and 1, or 0 and 100%, depending. Some programs give, I think Excel gives a percent, puts this in a percentage. That's fine. I think Minitab does also. It goes between 0 and 1, or 0 and 100%, depending on the program. What percent of the variation of y is explained by x? This says 94% basically of the variation in gas mileage can be explained by how fast we drive this car. That's very, very high. That's very, very high. So that shows that this is a very, very adequate model. So now let's go ahead and look at, so we looked at the p-values for the slope and the constant. We looked at the r squared. The last thing we'll do is we'll look at what are called the residuals. We want to evaluate the adequacy, or we want to validate the model. I'll show you how to do that. As soon as I can take off that. There we go. In Excel Stats, it's looking at residuals analysis. We do the we validate the model by looking at the residuals. And here, what we do is we want to see that, for example, that the residuals are more or less normal, which certainly looks like they are, and that we don't see any clear patterns when we look at the residual versus predicted value. And here, again, to me, there's no real clear patterns that are coming out. In the book, I talk about what's called the 5-second rule that I use. It's kind of like dropping a cookie on the floor. If you don't see a real pattern coming out, then there's nothing that's really violated, and your model is reasonably valid to go ahead and move on. Okay? And that's it. So now we've done all of the first three things, and we've done it pretty quickly. Let's do the last thing, which is actually go ahead and use the fit to make model predictions. And essentially, it's simply plugging in speed and getting a gas mileage that comes out, because now we have an equation, a functional equation. So if I want to know, for example, what speed, if I drove 60 miles an hour, what gas mileage would I get in this car? What would be my prediction? I can actually come down here and do that. in Excel Stats, I type it here. And this tells me that let me remove some decimal points. Makes it hard to read. Right? There we go. That's a little easier to read. If I drive 60 miles an hour, I would predict I get a gas mileage of 22.8 miles an hour. And if I wanted to hem my bets and give a confidence interval, in this case a prediction interval on that, I would say, well, I would be pretty sure, 95% sure, that I would get between 18.7 and 26.9 miles per gallon if I drove at 60 miles an hour. Okay? So you can see that what we did was we went on let's do a quick recap. We made a plot, we fit a line, we checked to make sure that that line was a reasonable model, we checked the adequacy by looking at the R-squared, we checked whether it met the assumptions by clicking on the residuals, and once we were satisfied with that, we went on and we made predictions. So I could predict, for example, of what would happen if I drove 50 miles an hour, or what would happen if I drove 45. Okay? And it just gives me different gas mileages that the model would predict. Now that I know it's a good model, I can go ahead and use it for prediction. Okay? So hopefully that made sense to everybody. And in the book, we give a lot of gory details on all the rest of that. I think that if it's okay with you, I'd like to do another example here. That was mileage versus speed. And if we do another example, we'll have a few more sort of under our belt. So we can look through the book, but I'd rather just cover what would be in the book instead. So let's do another example here. Let's do an example of this is one that's not that you don't have the data file for. Let's do an example of AQI, which is Air Quality Index, and this is looking at the air quality index of a number of different towns that are various distances from the city. So what we have here is we have let's see. Oh, I see. I must have deleted it. There we go. So what we have here is I have air quality index, or AQI, as a function of distance. And I want to see if I can build a model. Looks like this is a num, and this is a num. I want to see if I can build a model that helps me predict what my air quality index would be given the distance. Or I could predict for different distance. Let's say I wanted to move a facility, or I wanted to move my family. And I might want to say, well, where should I move my family in terms of how far away from the city should I be if there's, say, a chemical plant there to get good quality air. Let's take a look at that and see if we can make some predictions. Okay, so as I said, the first step Can everybody hear me? I've gotten notices that my
You just
network
came back.
Yep, you just came back, Mark.
Oh my goodness, how long was I out?
The last we heard was you looking at the data and just telling us that it was air quality by city, and that was the last we heard.
Okay, it was only a minute or so, 30 seconds, so apologize for that. Great. So let's suppose that if we were looking at air quality by city, and you saw that these are two nums, for example, I might be interested in predicting if I moved my family so far out of the city, what would be the air quality? So I'm just trying to establish maybe a usefulness of looking at this model before we jump in. So again, let's remember the first thing that we need to do is plot. The second thing would be to build the model. Build. The third thing would be to adequacy, to check adequacy. Then validate. And then finally, if everything is okay, use the model. Okay? We'll see how far we get on this one, and then we'll maybe do a couple more examples. I want to show you this because it's something that we will be able to overcome soon, but right now it may give us some fits. Okay, as we know, it's num. Replace the data in that and take a look at the, well, that didn't work so well, did it? I know why. Let me close down my num. Okay, so there's my 2num analysis. All right, so I'd like us to take a moment and look at the scatter plot. And here's what I want you to, first of all, let's get air quality as my y, distance as my x. Okay, and I want you to analyze this scatter plot. So take a moment and think about the following. One is, one is look for outliers. Number two is look for the form. What's the form of the relationship? Is it a line? Is it a curve? Number three, direction. And number four, strength. Okay? So when I'm talking about distance in city and the air quality index, I want you to look for, are there any outliers in this plot? What's the form? Is it a curve? Is it a line? Is it a pumpkin? I don't care what. Describe it to me. Tell me what the direction is. Is it going up, going down? And then how strong it is, do you think? Okay, so take 15 seconds to think about that. Okay, I'm going to ask for a volunteer now. Who would like to help talk through their analysis of this scatter plot?
I'll take it, Mark.
All right, go for it.
This is Brad. It looks to me like it curves off and it tapers out around an 8 or a 9 the further away you get from a city.
Okay, great. It certainly does look like that. If we were going to go through, would you mind kind of going through the process on the right-hand side that I kind of outlined? Just for folks who didn't quite were able to kind of leap through that. I would tend to agree with you, but let's kind of walk through that, okay? Would that be okay with you?
Yeah, absolutely. So the first question I had is that one data point off to the far right, is that an outlier or not?
Okay, excellent.
And just by looking at it, you can say that it is, but if you think about what you're modeling, you would certainly expect to see kind of a curved slope as pollution dissipates. So I went ahead and said that it was not an outlier, and it is indicative of the shape out there, but we certainly don't have the data to say that's, for sure the major thing.
Got it, right. So that's a good question that comes up, right? If you were just kind of blindly fitting stuff, I mean, what if you got another point and it came out right here? Now all of a sudden it's looking a little bit like an outlier, isn't it? Or maybe this one is. Hard to say which, right? So that's a good point. So I think that's a good, it's a good place to start on that one. And
since we're talking through that, I mean,
yep.
The other thing I'd be interested in is what distance do I really care about? Because if I'm trying to commute to this city, I don't want to live 200 miles away anyway, so I probably don't need a curved fit on this data. Probably a simple line would be enough for my needs here.
That's right. It might be fine if you're just fitting to this portion or whatever. Right. So that's a great, I think that opens up the two great comments or discussion points, and that is, we fit the models. Models are going to be useful in different areas for us. Remember, a model is just a model. It's just something that's supposed to help our decision making. It's not reality. So we do our best at that. So just a quick comment. Certainly, if we saw a point over here, that would be an outlier. You'd want to check that out, and so forth. Okay, great. So good. We're good so far.
So the overall direction, you would say that there's a positive correlation, and since the data is pretty close together, I would say that there's a high degree of strength as well.
Okay, got it. Excellent. So I'm going to go ahead and draw. I mean, you originally had said there's a curved relationship, and it certainly does look fairly straight, and then maybe curves over like that. I think that's what you were talking about. So it certainly has a good
Correct.
line right there. And yeah, those data points look pretty close. They look pretty close. And the direction, ask the question this way: as distance from city increases, what happens to air quality? It tends to increase, right? So increase and increase is kind of a positive direction. Okay, good. If you can go ahead and you don't have a problem interpreting scatter plots, you can go ahead and jump into it very quickly, just like Brad did. If you don't and you're not used to it, I would suggest using this form of going through 1, 2, 3, 4 as it's outlined on page, in your book. This is slide 9. Slide number 9, I give you a little process for examining a scatter plot. If you're already comfortable doing that, by all means, go ahead and do it. Okay, so let's move on to the next part. We're going to fit our model. Now, normally, if we wanted to fit our model, I'm going to show you an example of what's going to happen. When we have a curve here, we don't yet know how to do that. That's what's coming up, and we'll be able to discuss that in the next lecture, at least part of the next lecture. Okay, I guess Microsoft canceled. That's not good. Having technical difficulties here. Sorry about that, folks. There we go. It looks like it just shut down. It's okay. I'll redo it in no time. Almost no time. Okay, so here's my to-num. And there we go. That's where we were before. All right, so let's go ahead and build the model. So as we build this model, you can see that that curve is kind of a little bit of a squirrely fit, but it still comes over here, and if we look at the model adequacy, there's the slope, there's the constant. By the way, usually statisticians are consistent folks, but we're inconsistent when it comes to constants in regression. The convention is to leave the constants in, even if they're not significant. Okay, so we're going to leave this term in our model. I'll show you a quick example afterward where we'll have a term that doesn't get left in the model. Okay, so here's the fit that we have right here, and you might say, if you look at the adequacy, there's a 78% R squared, but again, I'm getting already a little bit uncomfortable just going over using this model. If I were going to fit to a lower, I maybe wouldn't leave that dot in the fit, or I take that out of my data set to fit the rest of this, and only use the model between, say, 50 and 150 kilometers from the city. It happens to be from Australia, so they measure in kilometers, not miles. This ought to be something that is kind of a red flag. Even though it's a reasonably strong model, now we go in and we check our residuals. And, oh boy, first of all, look at that normal probability plot. Doesn't look like a straight line. And secondly, if we look at this guy, it certainly looks like there's some patterns going on here in the residuals. It looks kind of like a little bit of a roller coaster. That's a little bit hard to tell. I certainly think that this is a little bit easier to tell. So, in terms of the adequacy of the model, I bet we could do a lot better by fitting a slight curve to this. And we don't yet have those techniques. Okay? But if you wanted to go ahead and use this model, you might be able to use it for, over a small range right here. And you could use it for predicting, for example, what would be 150 miles from the city. This would say my air quality index is about 7.4, and maybe that makes some sense. That would be right here. It's predicting at that line. Okay, 7.4. All right, so that's that one. Now to show you how much better we can actually do by fitting that, I'm actually going to fit something that's a little bit different, and we'll learn this next time. I'm going to fit a polynomial, and look at this. Here's a 2-degree polynomial, and that fit is almost a 90% R squared. So this would be a much better fit for our data than we had before. Again, as long as this is not a big-time outlier, this makes some sense. All right, but that's next time. We'll learn how to do that. Okay. Okay. So I'd like to do a couple more examples, and you can go through all the examples in the book from the slides, but hopefully this gives you a good idea of the progression of what we need to go through in order to make this work. The slides also use Minitab in their examples, which is a little bit more of a power tool for doing regression. Excel Stats is great for doing one X and one Y, but when you get into more than that, it gets problematic. So if you have the book, what I'd like you to do is let's turn to, I'm going to do the example that's called exercise 42 on, I'm sorry, that's called exercise 1 on slide 42, and that involves the forms data set. Apparently forms is a small data set. Okay, so in this case, this is a case where a company wanted to know, among other things, they have a company where it's a transactional process and they measure the cycle time or the processing time of a certain form. Okay, that certainly is a num. And they have a number of different things that they might want to use to help determine how fast. They have a couple of drivers. One of them is the number of fields, which is also a num. And another is the type of form, which is a cat. Okay? Now, we're not ready yet to do multiple regression and understand how to put both of those in our model. Let's walk before we run. So let's see, let's examine fields versus processing time, and let's see, does the number of fields actually make a difference in processing time, and by how much? So let's go ahead and do that. The process that we're going to use is 1, plot, 2, build model, number 3, adequacy check. That's R squared. Number 4, validate. That's residuals. Whoops, that's residuals. And finally, predict. Okay, so let's go ahead and do that. I'm actually going to ask for a volunteer to help me walk through that. Brad, you were very helpful in that. Who would like to volunteer to help me walk through that? Or should I consign somebody? Sign somebody up. Okay. All right, Patrick. I'm going to give you the controls.
Whoa, whoa! I don't need my controls.
Oh. What's that?
I don't know if I'm good enough for controls yet.
Oh, okay. Well, I'll tell you what. All right, I will
Try
say.
it. I don't care. I'll go for it. Why not?
You want to go for it?
Yeah.
Okay. Let's go for it. Okay. So the first thing is, let's make the plot, and let's go ahead and use Excel stats, since I know a number of people have this. So I've got Excel stats open, so you can use my computer and my data form or my data file right here. So first of all, can you move your mouse and make mine? Yeah, oh, excellent. All right, good. So the first thing is let's take a look at the plot. Let's do that scatter plot.
Okay. Yeah. See, this is how I do it different with Excel stats. I don't go straight from. So I just usually copy and paste. So if I'm going here, do I just go that route and go through stats?
Yep.
Okay. And tune them.
Got it.
Okay.
All right. So let's spend a little bit of time analyzing the scatter plot. What is it that you see?
I mean, there's, I guess, a slight movement, I guess, from the bottom left up to the top right, but nothing that's very clear. I wouldn't say it's very tight of a correlation between the two. So that's just right off the top of that what I see.
Okay, great. So, you know, again, if I'm going to go through my 4 questions, it's going to be, first of all, I'm going to look for outliers, right? Does anybody see any outliers?
Yep.
Yeah, look at that one. So that's definitely a point I'm going to check out, make sure somebody didn't fat finger it, you know, things like that. Outliers are great to help you understand real anomalies. It's also different if we found something that was like way out here. That would really be something that we'd want to look at because it kind of violates the model. As it is right now, the model that we're kind of thinking, I'm gonna see if Patrick, you can disagree with me, but it's kind of this model is what we're thinking of, right? And yeah, and it's kind of loose right here, right? Okay, got it. All right, so far so good. So that's the model that we're thinking about building. And also, just to ask you I guess to be overly blunt about it, where would you feel more comfortable using this model? Would you feel more comfortable using the model here or on the right-hand side?
Down on the left-hand side.
And why is that?
I just feel like there's more data there.
You got it. That's right. So wherever the data are very sparse, we're going to hem and haw about using our data, about using the model. We're not going to be as comfortable. I'm not going to be as comfortable using my models in a case like this. You know, maybe this isn't the anomaly. Maybe this is more the normal data point right here. Maybe the next data points will be around here and here, and it'll indicate some sort of curve. I'm not so sure. I don't have a lot of data. Okay, good. So that's exactly what we wanted to talk through. Good. All right, I'm going to see if I can give you back the controls. Okay, let's go ahead and now build our model. Luckily, it's already built for us. We just have to kind of look at it. Do you remember how to get there?
I do not.
Okay, it's on Correlation and Linear Regression tab. Okay. We can, first of all, Minitab puts the Excel Stats actually puts the picture in there, and it builds that model. You see that picture right there?
Yes.
Yeah.
Got it?
Okay, good. Excellent.
Didn't we do the slope and changed it down here to the...
Yes. And I apologize for that. I wish it would have been there, but even when we put in the not equal, looks like the p-value is pretty low or high?
Very low.
Pretty low. And same with the constant. So we're going to keep them both in. So it's a significant model. There really is a relationship between those two. There really is one.
Then you look at the R-squared, I guess, is the next step, and that is, I guess, would cause some worry. Now, what that says is that half of the X is predicted by the Y, or the other way around?
Other way around. Half of the Y, half of the variation in field. Oops, we've got it backwards, don't we? Oh, we've got it backwards. Let me change this around. See, I should have been smart about this. There we go. That's what we want. We want to predict the processing time by looking at the number of fields, right? We want to have X here and Y here. I'm sorry I didn't notice that before. Sorry about that. So go ahead and say what you were saying.
No, I just
Yeah, right.
the R squared, there's not a lot of, I mean, it's only predicting half of the movement of the variable.
That's right. So if we really wanted to nail to a high degree what processing time was dependent upon, we got about half of it here. That's not bad. That's actually pretty good. But if we wanted to build a really tight model, we'd have to look at additional variables.
And that's
Okay.
the residual.
Yep. Let's check out the residuals. Okay. 5 seconds. Oh, go ahead.
I was going to say you have a fairly tight line here.
Yep. Looks pretty good. Looks pretty normal.
Now this up here, I never really kind of understood what you're looking for in this piece up here.
Okay. So what we're looking for is we're looking for quote no patterns. Now that's a weird thing to look for, is nothing. But here are some typical patterns that we might see. We might see patterns that look like, let me erase this here. We might see in our residuals versus predicted, we might see a pattern that looks like this. I'm going to exaggerate this, but this might indicate that we fit the wrong form of the equation, right? Like if we had a really super duper curve, but we didn't fit it, we fit it with a line. That we might see something like that. That would certainly be a pattern to the residuals. Do we see something like that? Not to my eye. I don't see any. Here's the other one that you really want to look for, and this is called non-constant variance. It's almost like an alligator that's opening up its head, where on one side it's very small, and as Y increases, you see the residuals increase like this. So it's sort of like a cone pattern. I often think of like an alligator or something like that, some jaws that are opening up. And this is called non-constant variance. And this is often it means that we'll want to look at what's called a transformation. That's definitely a black belt technique. But would you say you see this or don't see this in that plot there?
I do not see any kind of pattern.
Good. And I would tend to agree. What I have is kind of, as I said before, the 5-second rule. So I mentally, in my brain, say 5, 4, 3, 2, 1. And if nothing really pops out at me, basically either of those two right-hand patterns, then I'm good. I'm good to go. So it looks like the assumptions are reasonably met. By the way, the assumptions are that the residuals are normal. And that they're not serially related to each other.
Okay. So do we shut this down at this point? You got it.
Oh yeah. Well, let's go ahead and make a prediction. And I'd like you to predict. Oh, let me go to here. Yeah. Let me go ahead and ask you to predict what would be the processing time if you had 12 fields in your form.
And that would be the 39-minute
Right.
time?
That'd be 39 minutes, but I want you to take a look at that interval. It says it's 39 minutes, but look at what the lower and upper could be. It could be anywhere between 12 and 68 minutes. It's a pretty darn wide interval. And by the way, the same would be for the 23, an extremely wide interval. And that just really reflects, well, the model isn't really adequate to give you tight predictions, so it's not going to. Does that make sense?
Yep.
Okay, yeah, so when you have a tighter model, you're able to do a pretty tight prediction. When you don't, you can't. If you want to see a picture of that, you can click on the confidence and prediction bands picture, and it'll actually put up the prediction interval for you. So for at each point here, in your model, you would be able to say, okay, if I want to predict what if I had 20 fields, looks like it'd take me about 60 minutes, but plus or minus a huge amount. You know, anywhere from, I don't know, 25 or 30 to 100 minutes. That's pretty wide interval. Okay?
Great.
Okay, well, thank you, Patrick. Hopefully you've seen that this is not all that difficult to do, but it does take a little bit of making sure that you spend a little time to make some predictions. I mean, before you just go ahead and make predictions. It's the top of the hour. If you can stay, what I'm going to do is go through one more example, and it is the last one. You will be assigned to it for your homework. So if you can stay, I would advise you to do so. But if you can't, I certainly understand. This really gives us an introduction to linear models. What's coming next, and is well, we've done it for the simple case of one x and one y in fitting a line. Right? That's what we've done. So what we're going to do in next lecture is, well, what happens when I have, here's my y, what happens when I have two x's, x1, x2 and x1, right? Or 3, or 4, or 10. What do I do then? So that's called multiple regression. And we hinted at, you know, that's one of the keys to getting an adequate model. If you look at companies like Netflix or eHarmony, they claim that they use hundreds of predictor variables, hundreds of x's, to get a model for their y's. Okay, scary thought with eHarmony. Another thing that we're going to do is we're going to look at, well, what happens when we have curved relationships? Do we have any tricks that we can deal with if we have some fit that looks sort of like this? How could we fit this line if this is our x and our y? And so we'll look at two tricks. One is polynomial regression, and one is transformations. Probably we'll just look at polynomial, and we'll look at a video for, I'll make a video for the transformations or for both of those. But these are, like I say, these are bit sledgehammer techniques. So definitely black belt territory. Okay, so we'll look at those two. And then finally, we'll look at, well, what happens when one of these variables, say x3, we had all nums before. What happens when x3 is a cat? How do we build our model then? If we want to put in, maybe we have different models for males and females, or maybe we have different models for the type of form. Remember we had that? So maybe that would cause us to do some other things. All right. So thanks a lot for hanging in there, and hopefully the discussion about the assignment was helpful to you. I know it went a little bit slower than I thought it would, but having that dialogue with your plots is really and with the data that you've got, is really what I'm hoping to try and really get you to do more and more in this course. And Patrick, don't do too much with my computer. All right. I know. Okay, so I'm going to stick around and do the last example, but other than that, you should look for the assignment coming today, assignment 4, and we'll see you on Friday, and we'll see you in your one-on-ones this week. Okay, thanks, guys. All right, for those of you who are staying, I'm going to go ahead and do one more. I'm going to do the example at the end. And I'm also going to do show you what happens in multiple regression, why that building the model seems right now to be kind of a joke, but it won't pretty soon. So let's go ahead and first of all do the example. And by the way, feel free to ask questions while I'm doing this as well. Still have a few people on. Okay, I'm just kind of shutting down all of those. Let's take a look at loyalty score. So in this case, we're looking at a study that examines customer satisfaction and customer loyalty. So customer loyalty defined by numbers of repeat purchases, or maybe you could even say it's by an NPS score, who knows what. Okay, but it's some measure of customer loyalty, usually by some measure of repeat customers or referrals. So we want to see if oops, that's not it. We want to see whether loyalty, RY, is affected by customer sat. And can we use customer sat to predict? That's a num. That's a cat. Oops, I'm sorry, that's a num. Num num. All right, let's go to it. All right, we'll go through the motions again. Number 1, plot. Number 2, build. Number 3, adequacy. Number 4, validate. And number 5, predict. I'll put a question mark here. Because, you know, if we find that things are not adequate or not valid, we don't want to be making predictions, right? I guess that's I tip my hat on that one. So going through and doing it in Excel stats, 2-num analysis. Boy, here's our first scatter plot. And if you look at this scatter plot, it certainly looks like, oh man, I don't see anything in this scatter plot. Maybe I've got more data up here than down here, but it's really hard to see. First of all, I've got a lot of data points. I've got 864. So, but certainly I wouldn't say it's a tight pattern. The scatter plot's a little bit hard to read. But let's take a look and let's see if there is a relationship between these. Now, in the book, I talk about correlations, and it turns out that there is a significant correlation between these two. So here's the model, right, and here's kind of where we were getting at before, very similar to the previous example, but even a little more crazy, is that, boy, look at the p-value here. It says that slope term really is significant, and so is the constant, but that this is nowhere near an adequate model for making, or it's a very low adequacy model for making predictions out of. So we can basically stop right there. I guess I could do the residuals analysis to see if it's a valid model as well. I don't see anything popping out at me. This is maybe a little non-normal, but with this many data points, you often see such things. It doesn't really give me too much pause. But the key thing here is that, well, I would be really careful about making any sort of predictions from this model, but it certainly establishes that there's a relationship between customer service and loyalty. Now, just as we might expect, I know one of us has this project or has a project that's very much like this, so I'm not going to go ahead and predict. I won't do that. But one of us has a project, or two of us have a project like this. You're looking at, say, loyalty or some measure of loyalty. Yeah, customer sat has an input, but really what we want to know are all the drill downs into customer sat. Well, why is somebody rating us as a high customer sat, and what can we do about it, right? So we really want to find many, many, many more X drivers of this in order to build an adequate model. And by the way, that's probably a long-term thing that may never happen completely, right? But we may be able to build models for, say, customer sat to a much higher degree. It does still establish it as definitely real. That correlation is a definite real correlation. Okay? All right, so hopefully that that will help get you through the homework assignment pretty easily and pretty well. I'm going to do one more on multiple regression just to show you where we're going on this. I guess before I stop, I'm going to ask, does anybody have any comments or questions on that last example that we did?
Mark, can I just, did you say that with the p-values being low, there is a correlation, but because the R2 is low, we can't use it as a predictive model?
Yes, that's exactly right. So like in all hypothesis tests, when you look at a p-value, if p is low, the null must go. The null is always innocent. There's nothing going on. There's no correlation. Okay? There's no correlation. That's okay. Man, you're really trying to mess. I'm
going to write a nasty note to Brad, but he won't pay attention probably.
Okay. So it does say exactly as you interpreted it. It says that the correlation is significant. There is a significant correlation, but it says that there's a lot more to this model than simply saying loyalty is a function of customer satisfaction. It's a function of a lot more things too. Okay? Good. That's the right interpretation. So I'm going to open up one more, and this is the autos. And oh my gosh, you see, so there's a lot here. Suppose we wanted to predict, say, highway miles per gallon by a number of different things. And this one, you know what? I'll do Minitab because I'll stick with Excel. I'll do Minitab because we're going to use Minitab soon. But you can see there's lots of different things that are here. How about weight? And I'll just get into Minitab. So you can see how to do Minitab in regression analysis as well. I'm just going to pop it all in there first. And this is really just to kind of show you that, oops, fine. Okay. This is really just to show you that that building the model is simpler than just looking at one p-value. Because right now it just seems like kind of you know, it's kind of a joke. You just do it, you know, and it's significant. Excel Stats does it for you. All the rest. Oh shoot. Did I do the wrong thing there? I probably did. Oh, yeah, I did. Darn it. Try that again. Copy, paste. There we go. Okay. So now I'm going to build the regression model. In Minitab, as you'll see when you go through the book, it's stat, regression, regression. And they have lots of different types of things. Nonlinear, fitted line plot. So let's say we were trying to predict the city miles per gallon. Whoops, the city miles per gallon. That's our response. Ah. You can't blame Patrick for that. And I wanted to predict it by all sorts of other things like engine size, horsepower, revolutions per minute, fuel capacity, the length, the wheelbase, the width, the weight, and all that. Okay, I'm just going to hit the OK button. Clearly, there are a lot of other things that maybe we could look at that are in here, but let's just start out by these. And you'll see by looking at this, you see some of these, when you build this model, some of these p-values are not significant. So what we're going to do is we're going to systematically take some of these models out. Now look at width. The p-value for width is 0.296. So let me remove that, and you'll see the p-values for the rest of them are going to change. But this poses us with a different problem of building our model. Here's the full model that Minitab is building, maybe what we'll call the kitchen sink. But you'll see that the building the model is a little more complicated in this case. I'm just going to go ahead and remove that there. I don't want to remove a ton at once. I'll just do one at a time. Okay, so there's now length. Now I'm going to remove length. I can also do this in Excel stats, but I'm not going to right now. Now I'm going to remove, looks like horsepower is not significant. By the way, this is not the only way to do it. We'll discuss more or less how to, now engine size is not significant. That's interesting. Engine size isn't significant. I wonder why that is. We'll find out why next week or next Friday. Now it looks like revolutions per minute is not significant. And looks like everything else is. So we started with a very complex model, and now we've simplified it. And we can say that, for example, for this case, we've got an R squared of 74. We'll know what this is too, R squared adjusted. But an R squared of 74. And our model, which isn't bad, it's pretty good, and it says that we can predict city miles per gallon by a combination of fuel capacity, wheelbase, and weight, and they're all significant there, and that's exactly what that combination is. Okay, so that gives you a little more in terms of what we're looking for in the next section. And why the building of the model is a little bit more complex than what we've done thus far. Okay, but that's to come, and we will have more on that in the next lecture. Questions, comments? Okay, guys.
Mark, I think one word of caution is helpful with modeling, and that's to never use it to predict where you don't have data.
Well, I don't agree with that actually, because there are plenty. I think you should be very careful using it where you don't have data. But what are forecasting models, right? Forecasting models are exactly that. Forecasting models are we're predicting where we don't have data. We're predicting in future times. So that doesn't mean that it's not dangerous to build those to use those models. But I agree. I think that was Brad, right? So
yeah, that's Brad.
Yeah, I agree. That's a great comment, and that's called sometimes we'll do something called extrapolation, extrapolation is always a dangerous proposition. I wouldn't go as far as saying never do it, but definitely be very careful. An example that I sometimes give is if I look at sort of what was it? Bagels left. I give an example of a university office where they were looking at bagels, and they were looking at dollars in the till, in till. I don't know if that's the right, in cash register. How about that? So they had a cash register where people were paying for bagels, and they wanted to see if there was a function of the number of bagels that were left in the bin, if it was correlated to the amount of money that they had. And sure enough, I have people build a regression model that looks like this, and then I have them predict, well, what would happen if you found $130 in the till? And some people are predicting, well, I'd have negative 50 bagels in there. No, you wouldn't. You'd have 0. So that's a great example of saying, hey, let's predict where there's no data, and that would be a very bad one. So the point very, very well taken. Point very, very well taken. Okay. Any other terrific comment? That was a great comment. It's hard to follow that one, I got to say. Okay. So for those of you who hadn't turned in the homework yet, good luck. And if you have any questions, don't hesitate to call. Okay. All right. We will see you on either in your one-on-ones or next Friday. Thanks for all your comments. All good ones. See you, gang.